Let's look at another example. This time we're going to look at the rate that a distance is changing. So we have a man walking north at 4 feet per second from a point P, and then 5 minutes later a woman starts walking south at 5 feet per second from a point 500 feet due east. And we want to know what rate the people are moving, at what rate they're moving apart 15 minutes after the woman starts walking. So step one, draw our picture, and this picture shows when the woman would start walking. So the man has that 1,200 foot head start. So that's what this shows. It shows that the distance between them, and by this line segment, points that represent the man and the woman. And this is going to be changing as this point moves south and this point. So if you set this up algebraically initially, you would have a vertical line segment at x equals 500 representing the woman's path, and the point as t moves, as time goes on this vertical line is x sub w, y sub w, and then the point tracing the man's path would be x sub m, y sub m. So let's look at what's happening here. What we're going to want to look at is how this line segment, the distance between these 2 points, or the length of this line segment, is changing when 15 minutes has elapsed. So that means that the woman's gone 4,500 feet in the southerly direction and the man's gone 4,800 feet north. So if we set the relationship between the quantities up, we want this distance, which we know is by the distance formula. So the distance between these 2 points as they move in their paths is given by the distance formula. Since the y values are all the only thing that's changing, and the distance between the points along the x-axis is a constant 500, this is a relation we have. 500 squared plus the difference between the man's y-coordinate on his path and the woman's y-coordinate on her path. So you can see that this gets kind of messy doing it algebraically like this, because the path of the man is actually given as a line with a independent variable of time, same as the path for the woman. And then putting that in the distance formula just gets kind of messy. So there's another way to look at it that would simplify things. So notice that as time goes on and the man and woman are moving apart, that distance between them is also the length of the hypotenuse of a right triangle, where one leg is that constant 500 feet them along the x-axis, and the other leg is actually the sum of the absolute values of the distance the woman is from her starting point and the distance the man is from his starting point. So instead of trying to create the scenario we had in the last slide with parametric equations of involving t and the distance formula, what we can do instead is set up as the relationship between the quantities as a right triangle using the Pythagorean theorem. So notice that now we don't have to have any equations of lines anymore. So our relationship is given by the Pythagorean theorem. This hypotenuse squared equals 500 squared plus this side length. And that side length, like I said before, is just the sum of the absolute value of the distances that each has gone on their path. So step 3, we want to differentiate the relationship that we found. So that's pretty easy. Differentiate this implicitly. Since 500 is squared as a constant, that term goes away. So we have 2d times dd dt equals 2l times dl dt. So what we're looking for is this quantity. So now step 4, we want to figure out what it is we're trying to solve for and plug in what we know. So dl dt is the rate of change of this side, and that's simply that can be determined from the rate of change of the way the man was walking and the way the woman was walking. So if I add the absolute values of each of their rates, so he was walking at 240 feet per minute and she was walking at 300 feet per minute, so this side is changing by 540 feet per minute. And then at t equals 15, which is the time that we're interested in, side L is going to be given by the distance that the man has walked from that t equals 0 time and the distance the woman has walked from t equals 0 plus this 1,200 foot head start that he had. So that gives us 9,300 feet. And then also at t equals 15, we can determine the length of the hypotenuse just by simply using the Pythagorean theorem. So notice I'm in feet per minute here. So then the last thing is to plug in the known values and the instant values. So plugging in my values of d and dl dt as well as L, I arrive at 539.22 feet per minute. And that is 8.99 feet per second. So that's the rate at which this point and this point are moving apart after 15 minutes.